Welcome to the presentation on the 68HC11 Serial Peripheral Interface. Here we have a block diagram of port D. It contains the SCI port and the SPI port. The SCI port is a Serial Communications Interface and it is an asynchronous port. The SPI is a Serial Peripheral Interface and it is a synchronous port. The SPI has 4 pins. The first is a slave select pin, the next one is a serial clock pin, next master out slave in pin, and finally the master in slave out pin. Depending if the 68C11 is configured as a master or a slave will depend as to what the functionality of these last 2 pins are. If the 68C11 is to be in charge of the serial clock line, meaning it's controlling the timing of the data that's being sent out or received, then the 68C11 needs to be considered or configured as a master. If it's not in control of the serial clock line or the timing of the data and the clock line, again, if it's not, then it'll be configured as a slave. Here is another block diagram of the internals of the SCI port of the 68C11 as far as the port itself, all the data as to how it's being transferred and shifted, and the clock signals as well. But what I want to do is concentrate on a portion of that. Now here we have the shift register, which is up here. And as we can see, data is being sent out. This is being outputted, that's an out, and data is being inputted on the right side of the 8-bit shift register block. Now the other thing to show here is that if data is being received at the input, it could come from 2 places. It could come from here or from here. Now this again depends as to what the configuration of those 2 last pins were. And if data is being outputted, it can go to here or to here, again depending if it's the master or slave. So one of the things that I want to highlight is this, is that if we look here and slice this right in half, if your system is configured as a slave, the top pin would be your slave output and the bottom pin would be your slave in. But if it's considered a master, which would be right here, then the top pin would be considered a master input and the bottom pin would be a master out. Again, it just depends as to if the configuration of the SPI port would be that of a master or a slave. The SPI registers are shown here. First, let's start off with the Serial Peripheral Control Register, the SPCR. It's found at address 1028. The next register, the Serial Peripheral Status Register, the SPSR, is found at address 1029. And finally, the Serial Peripheral Data I/O Register, the SPDR, at 102A. Let's take a look at each one of these. So for the SPCR, the Serial Peripheral Control Register, we have these bits internally. So therefore, let's take a look at each one of them and see what we should configure this particular register at. Bit 7 is the SPI, which is Serial Peripheral Interrupt Enable. Well, I really don't want to use any interrupts, and so therefore I'm going to set that to a 0. The next bit is the SPE, which is a Serial Peripheral System Enable. Well, I do want to use the SPI port, so therefore I'm going to turn it on by setting it to a high, to a 1. Then we have the DWOM, the Port D Wired OR mode option for Port D pins, PD 5 down to PD 0. And if we set it to a 0, we have normal CMOS outputs. If we set it to 1, we have open drain outputs. Well, if you were to set it to open drain outputs, you would have to have some sort of external pull-up resistor in there, plus it having to be tied to a VCC. Most likely it would be plus 5 volts. But if you wired it, but if you had it set to a 0, which would be normal CMOS outputs, you wouldn't really have to do anything at the output because you would see already either a low or a high on there. So I would set this particular bit to a 0 so that we can use normal CMOS outputs. Then the next bit is the MSTR, the master mode select. And so therefore, my intention here is to be in control of the serial clock line, to control the timing of the clock line with the data being placed out there and being sent out, so that the receiving end would be able to receive it properly. And since I want the 68C11 to be in control of that, I'm going to set it as a master. So the master would be set to a 1. And we do have 2 other pins right here that we need to definitely spend some time on, which is the CPOL and the CPHA. This is the clock polarity and the clock phase. So let's take a look at those before we get to the SPR1 and SPR0. So in using this diagram here, we're able to figure out which CPOL and CPHA value that we need, whether we need to set them to both high or to both low, or one is 0 and the other a 1, or vice versa. But what we're looking here is looking at the clock itself as to the rising and the falling edges of the clock, and when the data is valid or when it's stable. One of the things that we need to do is we need to look at the receiving end. What are we sending the information to, and when is it going to be able to accept data? When is it going to take the data in on what part of the clock? Once we know how the receiving end is taking in data, then we can properly set up the CPOL and the CPHA. To do this, let's say that we're going to send this to a serial to parallel converter chip, such as the 74HC164. So let's take a look at that chip. The 74HC164 is an 8-bit parallel out shift register. And so it takes in data in a serial form and then outputs it in a parallel output. So let's take a look at the block diagram of it. And in looking at the diagram, and the term is actually logic diagram, we can see that we have a clock input, we have a clear input, but we also have 2 inputs. We have inputs A and B. And the reason that we have this is because one of the inputs can take the data in, while the other one can be used to either enable or disable the inputting of the data. And that's going into that NAND gate. And the parallel output is QA all the way through QH. So let's go ahead and jump to the part in the specification sheet where they talk about when the data at the input will be per se sampled. When will the input be triggered to take in whatever value is shown at the data input? In looking at the function table, one of the things that stands out, if we look under the column that says clock, we can see that the outputs are shifting on the positive edge, on the rising edge of the clock. So that's very important. So our data needs to be stable on the rising edge of the clock. So that's very important because now we understand how this chip operates at its inputs, and therefore we can configure the 68C11's SPI port to be able to place data and send the proper clock signal so that this chip will operate properly. So let's take a look a little bit closer at this diagram so that we can ascertain as to what the settings for the CPOL and for the CPHA should be. Now, one of the things that we know from looking at the spec sheet for the 74HC164 is that the input is going to be positive edge triggered. So therefore the clock is positive edge triggered, but the data needs to be stable then. So if we look at the positive edge, if we were to set the CPOL to a 0, if we're right here right now, if we were to set the CPOL to a 0, then the data would need to be stable on the positive edge, which would be right here. And if we look here, when is the data stable? If we're looking at something that's doing something like this, In this region right here, it's not stable. In this region over here, it's stable. And preferably you want it to be triggered or to be inputted right in the middle of that stable region. So in a sense, if we're looking again at this diagram, we can see that the data with a CPOL equal to 0, data is stable in this region right here. But it's not down here. Right here, it's not stable because it's just about to change, or it is changing. So therefore, if we were to set your CPOL equal to 0, then your CPHA would also have to be set to 0, because this is when the data is stable. Now, if we had picked CPOL is equal to 1, let me use a different color here. If we had picked the CPOL is equal to 1, then on the rising edge would be occurring right here. And if we look down here, if we set the CPHA to 0, this data is changing. But if we look down here, the CPHA equal to 1, that's when that data is stable. So if we were to set the CPOL equal to 1, the data is stable when the CPHA, and when the CPHA is equal to 1 as well. So basically what it comes down to is that you have a choice. You can set both your CPOL and your CPHA both lows, or you could set your CPOL and your CPHA equal to 1s. And it'll work either way, but only when they're both lows or when they're both highs, not when one is 1 and the other one is the opposite state. At this point, now that we understand the CPOL and the CPHA bits, let's take a look at the SPR1 and the SPRO bits. This right here stands for the SPI clock rate select. So let's jump to that table right quick. And here, depending as to what speed we would like to operate at, will depend as to what we set these two bits also. But one of the things that we need to also look at is, well, in most instances, we really want to operate as fast as we can. We really do. We want to operate as fast as we can. We want to be able to transmit as fast as we can. So one of the things that we need to look at is really, what is the fastest speed that can be received by this 74 LS164? So let's take a look at that. In looking at the timing requirements for the 74HC164, basically at about room temperature, which is 25 degrees Celsius, we have an F clock. This is the clock frequency. And right here, it gives us a maximum of about 31 megahertz. And this is really at the higher end. So as long as we keep our serial clock frequency below that, this particular chip will should be able to respond just fine. Now, looking back at our table, what is the highest speed? If it says now here, depending as to what the E-clock frequency is, what is the frequency of the E-clock? Well, since we're running an 8 megahertz crystal, and then it does a divide by 4 internally, our E-clock is running at 2 megahertz. So if we look into that column, the fastest frequency that we can actually send out information at is 1 megahertz. And this is way, way inside of the F max, which we saw in the spec sheet. So therefore, it will be no problem for that chip to handle a frequency of 1 megahertz. So we can set the SPR1 and the SPRO to both lows. It will be sending out over the clock a frequency speed of 1 megahertz, and that would definitely be acceptable at the receiving end. Now, looking at the serial peripheral status register, we have just a few bits to take a look at. We have the SPIF, which is the SPI transfer complete flag. This flag is set when an SPI transfer is complete. And we're to clear this flag by reading the SPSR when the SPIF is equal to 1. and then we access the SPDR. So this bit is very helpful in that it'll tell us when a transfer has been completed. So if we send out over the SPI port, we need to be attentive that we don't actually try to transmit immediately thereafter. And because why? Because it hasn't finished actually transmitting out what you told it to begin with. So we need to wait or pause to ensure that whatever we told it to send out has actually finished transmitting before we send it another byte. So therefore, we need to definitely check this SPI transfer complete flag to see when it's gone high, because once it's gone high means that the transfer is complete. Then we have the WCOL, which is the write collision, and this flag is set if the MCU tries to write data into the SPDR while an SPI data transfer is in progress. And we're to clear this flag by reading the SPSR and then access the SPDR. Again, if we did not keep track of the SPI transfer complete flag and we just sent it more data to transmit, we would definitely get what we call a write collision flag. And then we have the last bit, which is the MODF bit. This is a mode fault. And mode fault terminates SPI operation. The MODF is set when the slave select is pulled low while master is equal to 1. Clear this flag by reading the SPCR with mode F set, then write to SPCR. Well, in most instances, if you have it set to a master, you don't want to activate it to tell it that it's acting as a slave. And so that's what it's referring to here. Now, port D also has a data direction register, and this is found at address 1009. And there are several bits that we need to take a look at, which are DDR0 through DDR5, but mainly the ones that apply to the SPI port are the bit 2 through bit 5, the MISO, MOSI, the serial clock, and the slave select. So let's take a look at those. So for the DDR-D5, which is a master, therefore, if we set it to a 0, the slave select input to detect mode fault. And if we set this bit to a 1, the slave select is a general purpose output. And if it's a slave, if you configure the 68C11 as a slave, it'll always be an input. So we would set this one to a 1. The next bit is the DDR-D4. And if we set it to a 0, the serial clock output disabled. And if we set it to a 1, the serial clock output enabled. And if we're operating as a master, well, the master needs to be in control of the serial clock. So therefore, we need to have the SEK output enabled, so we'd set that one to a 1. DDR-D3, as configured for a master, if it's at a 0, it's going to be that the MOSI output is disabled. And if it's set to a 1, the master out slave input output is enabled. And if it's a slave, it'll always be an input. So as a master, we need to set this bit to a 1. The next bit is the DDR-D2, this for a slave. If it's a 0, the MISO output is disabled. If you set it to a 1, the MISO output enabled. If you're operating as a master, you always are going to configure it as an input. So therefore, this bit would be set to a 0, to a low, because again, the master in slave output is disabled, which means if the output is disabled, then it's going to be able to operate as an input. So therefore, again, this DDR-D2 needs to be set to a 0. And here's a sample assembly code. So let's follow this code. And as it states here, that this code transmits 1 byte of data out of the MOSI pin of the SPI port. So this 68C11 is configured as a master, and it's going to be sending the information out of the master output, out of the master out slave input pin. and let's follow it. So we're going to load accumulator A with a 38. That sets up the DDR-D. Then we load it with a 5C, which sets up the SPCR. And then we load it with a 01, and that's going to be sending out data over the SPI data register, which is at address 102A. Then we're checking that SPIF bit to see as to when it's gone up, because again, it's being transmitted. We need to check that flag to see if the transmit has completed. So we check it, and then once it has gone high, we can do whatever else needs to be done. But this small little program here is not, of course, complete. All we did here is just to show how we can configure the SPI port as a master and send out 1 byte of data and check to make sure that it has been sent out. After that, you can go ahead and send out some other bytes if you want, or you can wait for something to be sent, and so on and so forth. But again, this is just a very simple program that does exactly one thing. It just sends out 1 byte of data. And that concludes the presentation on the SPI port.